Okay, welcome back. For those of you who didn't get to see my face the first time around, sorry about that. Again, my name is Dr. J. Deanda. You can call me Dr. DA. And as I was saying earlier, I was born in San Francisco, but I grew up in Puerto Rico. My father was Mexican American, my mother was Puerto Rican. Got married right after college and went to the Boston area to get my PhD in biochemistry. What I didn't tell you earlier was that after a few years doing research, I actually left my science career. And for many years, I worked actually as a minister for an international church organization. I got to travel around the world. I have friends literally all around the world. It has enriched my life, and I love the exposure that I receive to so many cultures, so many backgrounds, and it makes up a lot of what I am today. Now, about 14 years ago, because of economic reasons, I decided to start kind of shifting back to other types of work. Along the way, I worked in the publications industry. I worked in nonprofit management. I even worked for a little while managing an investment fund. So I've done a lot of stuff. And but I love teaching, guys. I love it. I love the sense that I am putting stepping stones on the road to success of some people. So I'm glad about that. I'm sorry, but I was so kind of upset about this whole thing. I had to go get me some, they say that when the going gets tough, the tough get coffee. That's right. So I got me some coffee here. So if you don't mind, I'm going to sip a little bit. Thank you so much. And what we're going to do now is tell you a little bit about my teaching style. And we're going to cover the first part of our lecture. Now, originally, my plan was to cover the whole first part of Unit 1, but I'm only going to cover it partially because I really only planned to do this from 10:30 to about 12 noon, only about an hour and a half, because that's what a typical lecture is in my regular classroom. So let me go ahead and take us over here to our, let me set up my PowerPoint first of all. I'm sorry. Oh, no, I got it already. Sorry about that, guys. I am. Okay, there we go. Now remember that while I'm doing this screen sharing, I cannot see the chat box. So if you have any questions, just put them in there. I'll make some sporadic switches over, or maybe afterwards I'll check if you have any questions about the contents. One of the things that I like to do is I like to start the week with what I call a philosophy appetizer. And this one is about a word that I hope will define my relationship with you. It's the word trust. It means the firm belief in the reliability, truth, ability, or strength of someone or something. Okay? So here's my spiel here. I am going to trust that each one of you is here because you're trying to accomplish some goals in your life. You're trying to achieve some standards and something in life. And because of that, I'm going to trust that you're going to put in your best effort, that you're going to be honest with me, that when you communicate something to me, I'm going to trust it. I'm not going to question it. I'm not going to try to find some motivation. Oh, he's trying to get away with not doing the assignment or things like that. No, that's not my style. I'm going to take your words at face value, and I'm going to trust that you are doing this because you really want to achieve some goals, and that really drives you, okay? Now, in the same way, I want you to trust me, okay? I am here to serve you, to help you, to move you along, but teaching is a lot more than just communicating content to you. Because nowadays, a lot of the content that we're going to talk about, you can find on the internet. You can Google it. Hey guys, you can find videos online that are 10 times more professional, much better than the ones that I'm going to put out there. Okay? I am not a movie producer or anything like that. My goal essentially is to assemble the content in a sequence and in a way that's going to train your mind, the way you think. Hopefully someday, I mean, I don't know, you're going to remember all the rules about how to calculate the oxidation state of copper, or things like how do I balance a chemical equation. You know what? You might never do that again in your life. But I hope that the processes that you learn here will teach you how to look at the information the world throws out you. And this era we're living in with the pandemic, with all of the social issues we're facing, you know, there's a lot of information out there, and I want you to get trained in how to evaluate information and determine what the merits of that information is. Okay, that's really what this is about. So that means that many times the way I'm going to teach you is not going to be just kind of like you know, spoon feeding you stuff. There are times when you'll ask me questions and I might not answer your question directly. I might actually respond with yet another question. What I'm trying to do is I'm trying to make you think, because I know that in the end you will derive much more satisfaction and a deeper learning when you arrive at the answers by yourself. I'm only your tour guide. Okay. All right. So let's go back to our PowerPoint here. Oops, what happened here? Oh, where are we? Where are we? Okay. You can tell that I'm kind of amateurish when it comes to these technology things, right? Don't make fun of me. I know you have professors who are much, much more savvy at this kind of stuff, but hey, I'm trying my best. I got basically thrown into this online teaching stuff in a matter of 3 days. By the way, a lot of the stuff that you're gonna see here on the next few days is fresh. It's new. I'm making it as I go. As we go into our like 4th and 5th units of the course, a lot of that stuff is stuff that I did in the spring. So sorry, but I'm gonna have to recycle it. All right. All right. So let's go ahead here and let's begin with our first unit. This is an introduction. We're gonna talk about the scientific method, matter and energy. And in the lectures that are already posted, we're gonna talk about units of measurement, accuracy and precision, excuse me, and your favorite, dimensional analysis. Excuse me. Okay, let's take a journey into the mind of a scientist and talk about how we process things. I'm going to throw some things at you and just ask yourself, have you ever heard this? Oh, excuse me. Choked on my coffee here. Have you heard that Coca-Cola rots our bones? Have you heard that the Great Wall of China is the only man-made object that is visible from outer space? Have you heard that we use only 10% of our brain? Have you heard that children should be wary of evil people who put poison in Halloween candy? You know, these are things that are very popular out there. And yet the question I would ask is, where's the proof of that? Do we know this for sure? Is this information real? You know what? Let me throw some little more controversial stuff in here. That vaccination of infants can lead to autism. That human activity is the cause of climate change. That GMO foods are dangerous to our health. You know, these are issues that are being debated currently. And there's a ton of information out there. And what I'm going to say to you today, I'll say to you on the last day of classes also. Don't believe everything you hear. Question everything you read. Always be willing to ask questions and look at the sources and determine for yourself whether what you're hearing or reading is accurate or not, okay? And I'm not saying any of this is right or wrong, because that's not the issue here. I'm not talking right or wrong. I'm talking about the validity of information. You know, as humans, our brains are designed to gather information from our senses, like, you know, touch, smell, eyesight. then to process and integrate that information, and then act on that information. In other words, respond, run, laugh, or whatever. Here's a quote from Jeff Bezos. I know he might not be a hero to you or whatever, but it's a good quote. He's the guy from Amazon, by the way. The human brain is an incredible pattern matching machine. This is what our brain does. It takes information in, processes it, and then looks for patterns or trends so that we can predict outcomes, so that we can make choices about what to do next with that information. All right? So, you hear a joke, you process it. In your mind, you decide, do I get it or do I not? And then you decide, do I laugh at it or do I just, put a serious face and say, that's not funny? That all happens. You know what? The scientific method is simply a reflection of what the brain does. So we're not going to be here just to download information. As I said, a lot of this information you can get in Google. You can Google it. You can find it on the internet many times in much better formats than the ones that I'm going to give you. What we're here to do is to train our minds to learn how to evaluate, how to integrate, and how to apply the information that is out there. Let me give you a little scenario, and I know it might sound cheesy to you, and it's hard for me to do it without kind of like the visuals here, but let's say that you arrive at a party. All right, there's a lot of noise in there, and this is either in the pre or post-pandemic era, of course. But let's say you arrive at a party, the music is playing, the dance floor is full of people, the DJ is spinning his stuff there. There's this is by the way, a non-alcoholic party, so there's a fruit juice bar out there with all kinds of good stuff for you. You walk in, you're excited, and suddenly, out of the corner of your eye, you glance and you see there's a person kind of looking your way across from the dance floor. And again, your first thought is, maybe this person is interested in me. So you go through your different scenarios in your mind. They're interested in me, or maybe they know me from somewhere else, or maybe, gosh, maybe my shirt is all wrinkled and they're about to start, making comments to their, friends there about my wrinkled shirt. You go through all these scenarios in your mind, right? And then you decide to nail down that, no, they're interested in me. And so what you do now is you say, okay, I'm going to walk towards the fruit juice bar, and I'm going to see if they follow with me with their eyesight. So you slowly make your way there. You strut to the fruit juice bar, and you try to get a glimpse and realize, they were not even looking at you. They're looking somewhere else. Sorry, failed experiment. I know it's a cheesy illustration, but it illustrates essentially what the scientific method is about. And here's what it's about. Everything starts with observations, things that you take note of. All right? Once you have taken note of those things, you start looking for explanations. You start putting some scenarios together. Except that in science, we call that a hypothesis. A hypothesis is essentially an educated guess. It's kind of like a tentative explanation. You base it on observations, previous knowledge, and sometimes even like intuition. Now what you do is you want to test the hypothesis. You're going to conduct what we call an experimentation. Now, this is not like the first set of observations you made. These are observations taken under conditions that we can control so that we can ask and answer very specific questions. As you carry out the experiment, you collect more observations, but in this case, we call that data. These are the observations obtained from experimentation. Some data is simply qualitative, things like, colors or textures or things like that. But sometimes data has numbers attached to them, right? Distance, weight, stuff like that. After you've assembled your data and looked at it, you go back and see if your hypothesis was correct or not, and you may have to modify your hypothesis. But after several rounds of this, you arrive at something we might call a theory, a well-tested conclusion that can still be confirmed through further experimentation. Now, a theory is not necessarily a fact. It could be modified if new data surfaces that seems to indicate the theory has to be modified. Every now and then in history, people come across something that we call a law. This is a very consistent behavior that has universal validity. Now, you're familiar with the law of gravity, perhaps. In today's and this unit's lecture, we'll talk about something called the conservation of mass or the conservation of energy. And these are very important laws. All right? So that's the way the process works. Now, let's look at our subject here. On the stage of chemistry, perhaps the main actor is something we're going to call matter. Let's look at some definitions. Chemistry is the study of the properties and transformations of matter. What do we mean by matter? Okay, this is not physics, so I'm going to make it very simple. It's anything that occupies space and has mass. Again, I don't want to go into details about what the physics definition of mass is. Suffice it to say that mass is a property that if something has it, it is affected by gravity. So if something is affected by gravity, then it is matter. We don't work with matter in the universal sense. We work with substances. I'm sorry. A substance is a form of matter that has definite composition and distinct properties. When we say property, what do we mean by that? We mean a characteristic that can be used to describe a substance. There are two kinds of properties in general, physical and chemical properties, and we'll spend some time in a moment looking at those. Now, the other thing that chemistry studies is the transformations of matter, a change in the properties of matter, perhaps more specifically a substance, with time. And just like there are physical and chemical properties, there are physical and chemical changes. The fundamental concept of chemistry is the following: that all matter is made of extremely small units called atoms, and that atoms can bind together in specific geometrical arrangements to form what we're going to call molecules. The goal of chemistry is to understand the behavior of matter. This is what I call the macro world. This is what we can observe in our surroundings. Our goal is to understand the behavior of matter in the macro world by studying the behavior of atoms and molecules. I'm going to call that, for reasons we'll see later, the nano world. And the idea is that one side of that scenario, the macro world, is a reflection of what is happening in the other side, the nano world, and vice versa. As we observe matter, we can make different kinds of observations. For example, we can take note of what we call physical properties. These are characteristics that can be observed or determined without changing the chemical composition of matter. In other words, we don't have to change what the substance is made of in order to take note of this property. Some of these are qualitative, like color, shape, texture. Some of them are quantitative. For example, mass, the amount of matter; volume, the amount of space occupied by matter; or temperature, how hot or cold a substance happens to be, right? Now, one thing that's important, notice that, for example, you can describe the shape of a substance. You can say, well, it's cylindrical, or it's cubic, or it's, shapeless, or amorphous is the word for that. But you can also describe the volume. In other words, it's not the same. The volume is the amount of space occupied by that sample of matter. One of the most important physical properties is what we call the physical state. And in chemistry, we study essentially three physical states: the solid, the liquid and the gas. In the solid, like ice in this case, you have a definite volume and a definite shape that's independent of the container. When you see water as a liquid, you can see it has a definite volume, but it has variable shape depending on the container. Steam, which is the gas state of water, has both variable volume and variable shape that depend on the container. In our world today, there are other types of states. For example, there's what's called the plasma state. There's sometimes called the Einstein-Bose state. We're not going to study those because those are beyond the scope of what we can do in the lab. But let's do now something. Let's apply the fundamental concept. In other words, at the nano world, what does a solid, a liquid, or a gas look like? Well, as we can see, the solid substance, the atoms are packed in a very uniform and a very ordered array, very close to each other. And that explains why they retain their shape and why they retain their volume. Liquids, on the other hand, although particles are close to one another, there's some fluidity in them. They kind of slide past each other. And that's why even though they can assume any shape, they still retain the same volume. Gases, on the other hand, you can see the particles, whether atoms or molecules, are very separate from each other. They really essentially move about without concern for the other ones. And that's why they can expand and compress to fill a container of any size and therefore have any kind of volume. Another thing that our brains do is they classify things. For example, the physical properties of matter, besides qualifying them as either qualitative or quantitative, we can also classify them as extensive or intensive. Extensive properties are those that depend upon how much matter is being concerned. So it's kind of obvious, right? For example, mass, length, volume. Of course, the more water I have, the bigger the volume. Volume is an extensive property. On the other hand, intensive properties do not depend on how much matter is being considered. So density, temperature, color. So for example, if I have a can of paint, or if I have a bucket of red paint, let's say, both of those are red, and it doesn't matter how much paint there is, it is red. The color does not depend on the amount of material. Now, we know that we can change matter from one form into another. Physical changes are transformations in which the chemical composition does not change. Whatever substance I started with is the same substance after it undergoes this physical change. Applying our fundamental concept, we would say that the atoms or molecules that compose the substance do not change their identity during a physical change. Look at some examples. Crushing a cube of sugar, stretching a rubber band, boiling water to make steam. Again, the question you ask is the substance still the same after the change? Yeah, sugar is still sugar, the rubber band is still rubber band, and water is still water, even though it's in a different physical state. Physical state transitions are very important to us, and they have their own names. You can see this picture here. For example, the changing of a liquid into gas, like we said, boiling water, is called vaporization. The reverse of that is called condensation. You can see these over here. And you might want to study this chart. We'll refer to it later on, and we'll study these changes in more detail later in the semester. Okay, another way of classifying matter is by its composition. So matter can be classified according to whether it is a pure substance or a mixture. A pure substance is made up of only one component, and its composition is invariant. Every sample of the substance has the same composition. A mixture, on the other hand, is a substance composed of two or more components in proportions that can vary from one sample to another. Let me make a little pause here. At this point, of course, as I had said, I had promised you that we were going to cut off at noon, and it is noon already. So I'm going to go ahead and finish out recording the lecture. But if you have some other things to do, you're welcome to, leave now. Don't worry, you're not going to miss anything. Everything is being recorded, including this little interlude that I'm doing here. But feel free to leave. It's already noon. I'm sorry. I was hoping to do only like half an hour here, but I'm going to go ahead and finish recording the lecture, and I will post it later in your Canvas course page. Okay. So I'm going to go back. So if I don't see you at the end of this, have a great week. Please go ahead and make sure you follow that, study plan that I posted on Canvas for you. And don't get yourself behind your day-to-day study, okay? Trust me, it is very important to stay on pace, okay? And hopefully, I will have this recording posted, hopefully by later in the afternoon, maybe sometime after 3 o'clock. Here's the thing, guys. It sometimes takes a little while for me to upload videos because of my internet connection. So I don't want to promise it's going to be ready like right away, all right? So we will see you hopefully later on. Don't worry, I'm going to post more videos later on. You'll get like a weekly video from me. I don't know. I just want to make sure that I'm there for you. And of course, next week, I'll start having my office hours where I can interact with you on a one-to-one basis, okay? So if you decide to leave, that's fine. Just peace out. And I'm going to continue the lecture now for those of you who want to stay, and also for those of you who will be watching this recorded, all right? Okay, let's go back to our lecture. Okay, so we're talking about another way of classifying matter, which is not by its physical state, which is a physical property, but by its composition. In other words, what is it made of? In the case of substances, we have pure substances and mixtures. Now, we can actually do this. We can subclassify pure substances into elements and compounds. An element is a substance that cannot be chemically broken down into simpler substances. In the nano world, what that means is that an element is a substance that's made of a single type of atom. Not a single atom, sorry, a single type or kind of atom. And we'll study more of that in chapter 2. A compound is a substance that's composed of 2 or more elements, and here's the important thing, in a fixed, definite proportion. In other words, any sample that you obtain of that compound from any source is always going to have the same elements and in the same proportion. On the other hand, a mixture is one where the components are not always going to be in the same proportion. Not only that, but you can have 2 kinds of mixtures. Heterogeneous mixtures are the ones where the composition varies from one region or part of the sample to another. If you go to the beach and you collect some, sand and water from the shore, right? After a while, the sand will settle to the bottom and the water will stay on top. That's a heterogeneous mixture because the composition on the top part of the sample is different from the composition in the bottom part. Some mixtures are homogeneous, though. A homogeneous mixture is one in which all portions of a sample have the same composition and properties. For example, if I take a bottle of vinegar from my pantry, I can see that all throughout that bottle, it all looks the same. However, if I were to compare that bottle of vinegar of, let's say, Heinz, with another from, let's say, Del Monte, for example, a different brand, the composition of those 2 brands of vinegar might not be the same. But each one of them in itself is a homogeneous mixture because within the sample itself, there is no variation in the composition. The components of a mixture can be separated by purely physical means, like filtration or evaporation, whereas the components of a compound cannot be separated by purely physical means. If you have a chance, I believe this diagram, this flow chart is in your textbook. So I would go back there and it gives you like like a flow chart of all these things we've talked about, and with samples of each. And also in the bottom, it gives you the nano world view. In other words, what is happening to either the atoms or molecules in those different kinds of scenarios there. Okay, so I'm not going to go through this. I'll let you guys check it out later on. Or you might want to print out this chart for future reference. As we discussed the composition of substances, we can also describe changes in composition. In this case, we refer to what's called a chemical change. This is a transformation that alters the composition of the substance. So for example, anytime that you burn fuel, like when you run your car, anytime you have fire burning, things are being transformed into other things. The rusting of iron is actually a process that's similar to the burning of fuel, except that it is slower and of course less dramatic. But in the process, the iron is converted into a different substance called an iron oxide. Some of my colleagues like to do this demo in class. I don't do it, but if you were to put a piece of potassium metal into water, you would find a very violent reaction here. There will be some bubbling, there will be some steaming, and actually the mixture might catch on fire. After the process is done, you'll realize there's no longer any potassium metal in there. It has been converted to a compound called potassium hydroxide. And a gas that was not present at the beginning, hydrogen gas, has now been produced. These are all chemical changes because the substance you started with and the substances you ended up with are not the same. In the nano world, the way this happens is that during a chemical change, the atoms rearrange, transforming the original substances into different substances. Therefore, when we observe matter, we can describe what are called chemical properties. These are properties that, in order to be observed, require that the composition of matter be changed. For example, let's say I want to see now how would aluminum and calcium behave when put in water in comparison with potassium. We actually call this property the chemical activity of these metals. But in order to observe whether the metal is active or not, I'm going to have to observe that transformation that we observe with potassium, which means that the metal is going to be converted into something else. And once more, hydrogen gas, which was not there at the beginning, is going to be produced. So we would say that the chemical activity of a metal against water is a chemical property. In order for you to observe it, the composition of the substance has to undergo a change. There has to be a chemical change. Okay, so now that we have this terminology down, let's do a little practice. I'm going to give you some scenarios, and I'll give you a few seconds to answer by yourselves to the questions. When copper metal is heated in the presence of solid sulfur, the sulfur quote-unquote disappears and the copper changes into a red solid. Classify that as a physical or chemical change. Tick, tock, tick, tock. Correct, it's a chemical change because the original sulfur and copper metal have been changed into something else. Okay, let's try this one. Copper metal is stretched to form a wire. Classify this as a physical or chemical change. Tick, tock, tick, tock. Right, it's a physical change because the question you had to answer is, if I started with copper metal, did I still end up with copper metal? And the answer is yes. In other words, the composition did not change. Very good. Let's try this one. Physical or chemical change. Milk left in an open container at room temperature turns sour. That might take a little more thinking because you might not be understanding of what it means for something to turn sour. What it is essentially is your taste buds would be detecting a substance that was not there in the beginning. Correct, very good. This would be then a chemical change. Okay, let's try now with physical and chemical properties. How about this one? Tin metal can be flattened into a thin sheet, like a foil. Is that a physical or a chemical property? Tick, tock, tick, tock. That's correct. It's a physical property. It's actually called malleability. And the reason it's a physical property is that in order for us to assess whether tin metal has this property of malleability, is we do it, but we end up still with tin metal. It hasn't been changed into a different substance. How about the next one here? Above 1200 degrees, aluminum turns from solid to liquid. Physical or chemical property? That is correct. It is a physical property. It's actually called the melting point, and it is going to be the subject of one of your experiments here on week 1. Again, the question to ask is, when the aluminum underwent this change, did it change into something else? No, solid or liquid, it's still aluminum. But speaking of temperatures, let's try this one now. The flash point of ethanol is the lowest temperature at which its vapor can ignite. Okay, again, that word ignite, which means catch fire, brings us to what the answer should be. This is called a flash point, and no, it's not this flash point. It's a different property, but of course, because observing this requires us to see the ethanol burning, which means turning into something else, this would be a chemical property. Okay, I hope those exercises give you some practice and a little clarity as to how to distinguish between physical and chemical changes and physical and chemical properties. One of the most important laws in our work is the law of conservation of mass. It says that during a physical or chemical change, the total amount of matter, in other words, the mass, does not change. We're going to apply this law in several of our experiments. Remember, when we looked at the chemical changes at the nano world scale, we said, the atoms are still the same. They are just arranged in a different way. That is the law of conservation of mass. Now, scientists collect information and process information in order to find patterns. But a scientist must also communicate this information so that others can benefit from the discoveries. How does the scientist communicate this information about the properties and the changes of matter and energy? Well, we need a language. In the same way that we communicate with a language, chemistry has a language. Now it's interesting, the way we learn a new language is by first finding out, okay, what is the alphabet of the new language? And then we learn how to put letters together to form words. And then we put words together to form, sentences, right? Well, we have the same thing in chemistry. This is our alphabet. It's called the periodic table. And beginning in the next unit, we'll start learning how it's organized and how to use it for our purposes. The periodic table collects the symbols of the elements and arranges them in a particular way, and we'll learn as we go why they are organized in that manner. Now, we're going to be learning a new language. So our alphabet is going to be the periodic table. The words, in this case, are going to be called chemical formulas, and the sentences are going to be called chemical equations. So, for example, I can write something like this. Al, Al. That's a symbol for aluminum. I can also write this one, O2. That is a symbol for a molecule of oxygen. I can also combine these two letters, quote unquote, and form something that looks like this. That is a chemical word. We call it a chemical formula. Now, if we'd like to express how did aluminum and the oxygen molecule combine to form this compound that we call aluminum oxide, we can write it this way. And this would be a chemical equation, and it is the equivalent of a sentence in the language of chemistry. Now, a little bit about the symbols that we use. For example, for the elements. The symbols of the elements are shorthand versions of the element's longer name. The symbol can have one letter or it can have two letters. But remember, the symbols could be derived not from the English name, but from their Latin or Greek name. So, for example, we don't write the symbol for sodium as S or SO. We write it as Na for natrium. Similarly, the symbol for silver is not S or Si, it's Ag for argentum, which would be the Latin name. That's where the country of Argentina gets its name. It's the land of silver. In the case of the chemical formulas, the formula is meant to describe the composition of the compound. Remember that a compound is a substance that consists of two or more elements, always in the same proportion. So what we do is we put together the symbols for the elements, and then we use subscripts to indicate the number of items or atoms of that particular element. Notice here we have H2O and CO2. And by the way, the O in H2O would have a subscript of 1, but we typically leave it unwritten and it's implicit in there. So let's look at something we observe in the macro world, water. There's a glass of water in there. So we say in our language, water. Okay, Spanish would be agua, right? So anyway, how do we represent water in chemical symbols? Well, one way we can do is what's called, what we have here in B, it goes H subscript to O. That is what we call the chemical formula. Notice that all it shows me is which elements are present in here and how many units of each. You'll notice that we don't have a 1 for the O because we typically leave the 1, kind of like implicit in there. Now, the chemical formula doesn't tell me how those atoms are connected to each other. So for that, we could use the next one here, the one that has H, line O, line H. We're going to call this a structural formula, and there are several forms of that. What you'll notice is that in the structural formula, not only shows me how many atoms of each element are in here, but it tells me how they are connected. In other words, this one shows me that the O is in the middle of the two H's. That still doesn't represent what the molecule actually looks like if we could see it. For that, we have the next model, D. Notice that in this one, we represented the O as a red sphere and the hydrogens as white spheres. Notice that this one gives us a little more information in telling us, number one, that the O atom is slightly bigger than the H atoms. And secondly, that the molecule doesn't have the atoms arranged in a straight line. It's actually kind of bent. This model here has a very sophisticated name. It's called the ball and stick model. Yeah, that's what we call it. In the lab, we have little boxes with these kits, and we can assemble these molecules, and they help us to visualize the shapes of molecules. Now, as we will learn later in the semester, a real molecule does not look like this. It doesn't look like, little spheres connected by sticks. It actually looks more like spherical clouds overlapping each other. And because of that, the last model here, E, is a more accurate representation in that it shows both the relative sizes of the atoms, the shape of the molecule, but also perhaps the way that those atoms are connected to each other by essentially overlapping these, what we're going to call later on, these clouds of electrons. This is called a space filling model, and you can find kits to use in the lab that use this type of configuration instead of the ball and stick. So that is our introduction to the course. I hope you enjoy it. And this is part one. All right, students, that is it for unit number 1, first part. In our next section, we're going to be talking about the way that we observe and record measurements of data in the lab. And there are some rules to follow. All of that is in pre-recorded videos. Please go to your Canvas page to access those. Also, sometime today, many of the assignments that are due this week, this first week, are going to be posting to Canvas. Please look in there, monitor it frequently, and please set yourself on a disciplined pace of study so that you don't fall behind. Very important, please pay attention to the due dates of the assignments, because if you turn an assignment in late, there will be a deduction. Please look at the syllabus for all the relevant information regarding that. Thank you so much for being with us. Once more, I apologize for some of the glitches that we had here. First of all, with starting the Zoom session, and then with some of the recording here that I had to re-record because the original recording did not work out. So please bear with me, and thank you so much for being here. I really hope you enjoy this journey. I know that sometimes students are a little intimidated by chemistry, but I promise you, I'm going to help you out, okay? Any questions you have, don't forget, you can contact me via the Canvas inbox, or via text message, or via my email address. Other than that, I hope to see you soon. Enjoy the journey, and thank you so much for being here with us. Bye-bye.